Well, let's go ahead and talk about the second homework set that we are going to solve today and solve some of the problems and take a look at the strategies to solve the rest. So this homework set has a lot more trigonometry or just some right triangle geometry, and it also has some beginning of Newton's laws, something a little bit about inertia, and also that F equals ma, Newton's second law, and it also touches on some concepts of projectiles. Let's go ahead and kind of jump in and take a look at the first several problems, which are often called riverboat problems or river flowing problems. And they're largely problems about some sort of a triangle. And this first one has a triangle that revolves around two different sets of units. So we can see right here in the problem that we have meters per second and we have meters. All right, and so we can actually make some vectors and triangles with distances like 306 meters. And we can also make another triangle with velocities, and velocities to the north or velocities to the east, and those will be with meters per second. All right. So before we jump in and do that, let's just kind of review some of our basic formulas that we started with last time, and then we will continue to do this time. First one I want to highlight here is just our constant speed formula. It's right here. And so for things that have a constant velocity, we say that constant speed is just change in our position, delta x, over change in our time, delta t. And the bar or the line right here over the v just means that it's a constant or an average quantity. Okay. Next thing I want to look at is these three equations off on the left-hand side. And so the first one is often called our displacement equation. It says that our change in our x, that's our position, is our initial velocity times time plus 1/2 at squared. This is an equation for motion that we developed in freshman year. Again, for those that have already had some calculus, or if you've had pre-cal honors, then you may have already had this equation and taken the derivative of it twice. This next statement down here is the first derivative of the equation with respect to time. So the change in our position with respect to time is called our velocity, or dx dt is our velocity. And if we take the derivative of the first term, we get t to the 0, which is of course 1, so I'm left with the initial. And then also the derivative of the second term, the 2 will kind of cancel out the 1/2, and then I'm left with at here. And so this is the derivative of that first equation. If we rearrange this equation right here, it becomes this equation, which is the definition of acceleration. One other thing I want to say is that through this process, we're assuming that the a here and the a here and the a here is a constant, like 9.8. It can't be a function of time itself. If it is a function of time or a function of velocity, then there's no simple path to that we have listed right here. You'd have to go through and actually figure out exactly what these equations would be for that specific situation. But certainly some things in life have beautiful constant accelerations, like when you drop something in the gravitational field. Over here on the right-hand side, it says equation without time, and that means if you solve for t in one of these equations and plug it back into the other, you can get this equation here where final velocity squared equals initial velocity squared plus 2 times acceleration times change in position. This is not even like a new equation. This is an equation people use sometimes and they don't have time given. And you don't need this equation. This equation comes from the other equations. And so you can very quickly and easily just use two equations over here to find some same unknown if you don't want to use this equation over here. Let's go ahead and take a look back at the assignment and then solve something here. So first problem here, we have a river that's flowing east at a certain speed, and a boat crosses the river from the south to the north, and it maintains a constant velocity of 12.8. If the boat was to point straight across the river, then it would not actually move straight north. All right, so here is my river that I'm going to draw, and I'm going to draw it flowing to the east. Okay, so I'm calling this direction here north. All right, so this direction over here is going to be to the east. All right, so I have some kind of flow to my, I didn't get in there, flow to my river that's going this way. All right, and I have my little boat right here that wants to go across the river, but it's being pushed down the river, okay, by the river itself. And so as a result, the boat is actually going to go in a different direction, isn't it? It's going to go like that. And it's going to make an angle that it is traveling at to the right and upward. I'm not sure why I didn't get in there. Stay in there. There we go. It's going to travel in a direction more like that, and that can, of course, just be the hypotenuse of a triangle. So I'm going to leave that triangle kind of in red, where I would have a length of this side, okay, and I would also have a length of this side, and I would have a length of this side. Now the boat's motors are trying to push it at 12.8 meters per second relative to the water, and the water was pushing it at 0.976 meters per second, if I recall, 979. Okay, and this phrase relative to the water is kind of important. Okay, that means compared to the water, it's going at 12.8, but the water itself is moving, the surface it's on is moving. And so as a result, if you stand on the shore and you watch it, then you actually see it go at this speed. And I'm going to call this c. C here not meaning speed of light, but more like Pythagorean theorem, a squared plus b squared equals c squared. And so I can simply do a Pythagorean theorem. This is a right triangle. Since one of these arrows points to the north, the other arrow points to the east, then I can find my third side of the triangle pretty easily. Once I had these three sides of the triangle, you could also find angles, right? We could find this angle right here, and I could say that the tangent of the angle would be the opposite side over the adjacent. Let me correct this right here. That number was 979. So this is 0.979 divided by 12.8. And if you take the second tangent or inverse tangent of both sides, you will find the angle. Okay, and that is the next part of the problem there. I also want us to say that you could form a similar triangle here. So if I change colors, I could also form a similar triangle, and I could say, hey, you know what? If I know that it is 306 meters across, okay, then I could form a similar triangle with the exact same angles. And I could say whatever angle I solve for right there in the velocity triangle, it's got to be the same angle right here. That has to be true because if it's traveling at 12.8 meters per second straight across, then every second it's going to cover the same number of meters toward the north. And the river is going to blow at the same number of meters toward the south. So this is the trajectory of its velocities, and this is showing its actual path it takes. But both the green and the red, one being velocities, one being displacements, they're going to have the exact same angles in those two triangles. So by finding the angle in the red triangle, I found the angle in the green. So let's go back here and look at the question here. Well, the second part of the question is how far downstream has the boat moved? So when I look at my problem and I look at my givens or my unknowns, I'm looking for this little piece of this green triangle. That's going to be how far downstream the boat actually moved. And because these two triangles are similar, there's just going to be a proportionality between these sides. So I would then, I would have found this angle right here, and then I would use tangent to find the opposite side here. Okay, and so we can set that up and we can say that tangent of the angle, and again, this angle is the same angle you found in the red triangle, is equal to how far downstream. I'm going to call it x right here, divided by 306 meters, okay, I think is the distance we were given. Yeah, 306 meters wide. And the wide here, it's important that that is the distance from north to south, okay, because the boat crosses the river from the south shore to the north shore, okay, as we have drawn right here. So the boat starts here on the south shore and goes to the north, and we're looking for this little distance right there, okay? So that is how you solve kind of number 1 and 2. It is very much just a problem of right triangle geometry. The next few questions are very similar. I will make a comment here on number 5. Students often ask a question on number 5, and it's almost one of reading comprehension or semantics. So we have a mouse on a conveyor belt, and he's running at an angle of 21 degrees away from the motion of the belt. But he ends up running directly across. So if we kind of look at how to work that problem together here, and I'm not going to work the whole thing, I'm just going to draw it. So if we have a conveyor belt, okay, and the conveyor belt is moving in this direction, then you ask yourself, which direction must the mouse be going? And the mouse, if it's right here, and this is a dotted line showing us the direction of the conveyor belt's motion, the mouse must be going in a direction like this, okay, where this angle right here is 21. And as a result of the mouse running in that direction at 21 degrees, the direction it will actually go is it will actually go in a straight line across this way, all right? Because however long my black ink arrow is pointing to the left and down, that leftward projection of the leftward component is exactly equal and opposite to the speed of the conveyor belt to the right. Okay, so that's kind of how that problem looks. So this is the actual direction that the mouse goes, but they want you to go find something like this side of a right triangle. And when you found that side of the right triangle, my black ink here is velocities, okay? And so when you found this right here, you will have found how fast the mouse is running up the belt, and of course the belt's going down at the exact same speed, which is why the mouse goes sideways only, because those two velocities are canceling one another out, or making the mouse move relatively not at all left or right in my drawing. Okay. Next one here on the bus is pretty straightforward and simple. Some of the questions like ridiculously obvious, like how fast is the apple traveling relative to you? If you didn't get the answer 0, that's amazing. Think about it more, okay, because it is. The next 2 questions, 9 and 10, I'm going to let you try your best on. We can review them in class when you get in class the first day of school and kind of flip through this. But they are something more about projectiles and just your point of view, your frame of reference when you look at it. Okay, let's move on to the second half of the assignment here. And for number 11, we're going to do a little preview work on this to make sure we understand this. So we have a block on an inclined plane. What this symbol right here means, there's no friction. If you don't recall this symbol from freshman year, it stands for how sticky the 2 surfaces are together, and we call it the coefficient of friction. Okay, so the problem says they are frictionless, and that symbol is a way of saying frictionless. There's an angle of 23 degrees in this problem here, and it is going to slope at that angle as it slides down the hill. It has an initial speed of 50 centimeters per second. It has a distance of 1.9 meters that it's going to travel down the hill right here. And we're also given some information about its acceleration. What they're going to ask for is the speed at the bottom. So one thing I want to do here for number 11 is I kind of want to make a list of what I know and don't know. I know this. This number was 50 centimeters per second. I'm going to convert that to meters per second so that all of the units match between velocity and acceleration, because acceleration was in 9.8 meters per second squared. I also know this. I know the change in its position is 1.9 meters down the hill. I also know something about its acceleration. Okay, this is given. Okay, and that is in a direction straight down. That's the way gravity influences it. When I look at the unknown quantities that I'm looking for this quantity right here. All right, and so when I consider these three quantities that I'm given, that I've taken these numbers out of the problem and I've now labeled them with VI and change in X and A, that's a really important problem solving step, because as I flip back to my equations now, I can glance at my equations and say, hey, I have an equation right here, and that equation has the three things that I don't know, and sorry, the three things I do know and the one thing I don't, and so I can use that equation directly to solve it. There's one complication in this problem that's going to prevent us from solving it right away, and that is that it's on an inclined plane. So just to kind of be clear with that, if you drop an object, let's say you take the same block that has 893 kilograms and you just let it go, it's going to fall this way and it's going to accelerate at 9.8 meters per second squared. However, if you put it on an inclined plane like this, that is not going to be the acceleration of it. And that is because some of the gravity is being balanced out by the hill. As it leans on the hill leans back and pushes back on it. And that is going to prevent it from moving straight in this direction. Okay, so some of the 9.8 goes this way and some of the 9.8 goes this way. What I'm trying to say a little more explicitly here is that if I take this arrow, and I'll make it a little bit longer. If I take this arrow right here of 9.8 and I make it, say, longer like this, and then I kind of clone it, and I make another one just like it. I then want to break it up and kind of project it onto the hill and see how much of it is parallel to my hill and how much of it is perpendicular to my hill. So let me see if I can just clone that with a right click here. That'd be convenient. But I forgot what that command is. I may just try another one. What if I just copied and pasted it, I think. Yeah, we'll just do that. And then we will paste it. Okay, so we got another one. Same line. Start with the long drawn out process there. And so then I want to take this and I want to say that little arrow there that represents a length of 9.8 meters per second again. Okay, 9.8 meters per second squared. I want to say how much of that, if I was to make a right triangle, how much of it would project this way. Let me color code this. How much of it would project downward and how much would project parallel to the hill. So this is perpendicular to the hill right here. So I'm going to call that my acceleration that is perpendicular to the hill. And then if I was to complete out the right triangle with a side going this way, okay, some of it goes parallel to the hill. Now, this is a geometry problem, it turns out, and it's not even a very difficult geometry problem. And what we have to recognize is we know the angle of the hill. Okay, so if the hill is at an angle, we said, of 23 degrees, then there's a similar triangle that is formed by the accelerations and also by the hill. Okay, so the hill I see is at 23. If gravity points straight down to the middle of the earth, this is a right angle. So the angle up at the top of this hill between the arrow that I made for acceleration and the hill, it's got to be a complementary angle to 23, or 90 minus 23. I think that's 67. Okay, so that's a 67-degree angle right there. But remember that this red arrow is perpendicular to the hill. So this little angle right here that I will color red for us, that must be complementary to the 67, or this must be 23. That's the exact same angle as the hill. Okay, and that's just straightforward little geometry with knowing that there's 180 degrees in a triangle or 90 in two complementary angles. So I'm going to take my sides of my triangle that have a, there was too many objects to grab. Let me try again. That'll probably work. So I just want to take those right there. And let me see if I can actually do anything I'm trying to do here. No, that didn't work. All right, whatever. So I will just redraw the triangle here quickly. Okay, so I have this side going down like this, right? And then I have this side going down like that. That's the A parallel. Okay, this is the A perpendicular. And if I add those two up as Pythagorean theorem, I'm going to get 9.8. Okay, meters per second squared. This is a right triangle like this with an angle right here of 23 degrees. So you can see that in this triangle, I know the hypotenuse, I know the angle, and what I don't know is I don't know these two sides, A perpendicular, A parallel. And in this problem, I only care about the A parallel because I care about how much this block is going to accelerate down the hill in the direction of this, or this 1.9 meters. Okay, that is the direction that it is heading. Okay, and it's going to move that way with an initial speed of 0.5 meters per second. Right, that's its velocity initial downhill. So as it's going that way, let me go ahead and solve for this at this time. And let me say that sine of theta, I'm choosing sine because A parallel is opposite of my 23-degree angle, right? So this is the opposite side, so I'm going to choose sine. So sine of theta is opposite over hypotenuse, or sine of 23 degrees is A parallel over 9.8. Right, meters per second squared. And I can use this right here to solve for my A parallel and actually get a number out of it, okay? So here in number 9, this 9.8 is important, but I want to make a note that what I want to use is I want to use the A parallel, which is going to be equal to 9.8 meters per second squared times sine of 23 degrees. Okay, as I just found the previous page. So what I did in brief review there is I took the 9.8 meters per second squared straight down, and I kind of decomposed it or broke it into two parts. And so how much of it's parallel to the hill and how much of it's perpendicular. And some of this work that we went through is, I'm going to say, not simple. And if you look at it and said, okay, I followed your math, but like, what the heck did you really do? And am I expected to do that in class? The answer is yes, but not in the beginning. That's a skill that you will kind of pick up and learn just by doing it over and over, because we do a lot of things on hills in class at one time or another. And you'll begin to learn just through memory and doing it again and again that if you know the angle of a hill, you always want to use the sine to find the parallel right here. And you always want to use the cosine, it turns out. Notice how this piece is adjacent to my 23-degree angle. That means I want to use cosine. So I would use cosine to find the adjacent piece. And that would tell you how much a block is, say, leaning on the hill. And that is often something else that we want to find. If you want to find out how much it leans on it. Because if there is friction, that will affect how much frictional force there is, which there's not in this problem, okay? But there will be in future problems. So now I have what I need to actually work the problem here in number 11. Let's go ahead and put in our little equation. So in the little acronym we learned last time of given, unknown, now I'm dropping in my equation. Sometimes I call this Galileo's equation, because I heard once that in Europe they still call it that. Galileo apparently used this equation in kinematics or motion quite a bit, because in the 1500s they had really lousy stopwatches. Water clocks were the best they could do, and so he used this equation as much as he could, because he had no real way of getting any good gauge of time. So whenever he could work a problem without time, he was loving that. So here I'm going to put in 0.5 meters per second squared plus 2 times my acceleration, which I haven't numerically calculated yet, times x, 1.9 meters. Okay, I got 3.83 meters per second squared for the acceleration. It is parallel to my math, right? And then I calculated here for the final velocity. I calculated 3.85 rounding meters per second. Okay, don't forget to take the square root once you get all these numbers multiplied and added together to find that final velocity, because it is squared right up here in the formula. Okay. Let's go back to our assignment and see what else there is to grab onto. Sailboat is a very similar problem here. This one is the first one. We have F equals ma. You see they give you a mass of a sailboat, and they give a force. That capital N stands for newtons, if you don't recall. Okay, newtons are the units we measure force in. Kilograms, of course, are a unit of mass. Okay, and it gives you a second force here of 45 degrees westward of north, or 45 degrees north of west. And it wants to know what is the magnitude of the acceleration of the sailboat. So we can look at this, because this is going to be another triangle problem mostly, a little bit of physics, but most of it is reviewing some geometry. And so we have two forces. One is to the east, okay, and one is to the northwest. And so the numbers are 28,600 newtons is one force, and the other is 79,400, which is much more force involved. Okay, so I get those numbers down here. Again, capital N is just the units on the forces, and 79.4. Let me actually put a direction here also. East. Okay, and this is northwest. We also have a mass of my boat. I'll call that with an M. Okay, and they give us the mass at 16,300 in kilograms of the unit. There's no direction after that, because mass doesn't point in a certain direction. Pushes and pulls, like forces, point in a certain direction. So let's kind of geometrically draw this. And let me kind of get some lines here. So this is a line that is going in this direction to the east. Okay, and then I have a second line that is going to go let's make it an arrow. I have a second line that is going to get a second push, and it's going to go this direction. And I'm drawing this line much further than I drew the first one. And the reason is because of the numbers that are associated with these. Okay, so one of these gets a number of 79,400 newtons. And the other one gets a number of 28,600 newtons. And the directions I made east, and the other one I tried to do approximately 45 degrees northwest. And when you're looking for the result of these two forces, the result has this really simple name. It's called the resultant. Okay, so the resultant of those two forces, you start where you started the first arrow and you draw to where the second arrow ended. Okay, and that right there is called the resultant. It's also called my net force. So as I kind of review Newton's second laws here, let me come back. Newton's first law is a statement of the law of inertia. You remember that? Remember that? Object in motion stays in motion. Object at rest stays at rest. Was acted on by some external force. Okay, so that's inertia. Now, the second law, number 2, actually quantifies that external force for us. This is not exactly how Isaac Newton recorded it, and we'll look at it in a full calculus version sometime later in the year as Isaac Newton recorded it. But for right now, we're just going to write A equals the sum or the net external force over M. So this little term out here again, this is actually something you see as a button in Excel as well. And it just means to sum or to add up. So I want to add up my forces. And I want to find out what is the total external force on the boat. And I want to divide it by the mass, and that'll give me the acceleration. Okay, that's how I'm going to solve this problem. So I have a green arrow. That is my net external force. I have a mass right here. So I'm going to divide that net external force by the mass. And I'm going to then have my acceleration. I just got to figure out the length of that green side. Now, I know some things about this triangle that can help me out. And we're going to try and solve it as a right triangle problem to make it even simpler. I know that this right here is 45 degrees. Okay, so this is a triangle. You kind of have a side angle side theorem here. And if you don't remember that from geometry, that's okay, because I'm not going to use a side angle side to solve it directly. I'm going to use Pythagorean theorem to solve this. I'm going to make it into a right triangle situation and figure out what is the length of that green side right there. So the way I'm going to do this to figure out the right triangle is I'm actually going to see what the horizontal component or projection is of my 79,400 Newton force that is at 45 degrees northwest. So that red line right there, I'm going to redraw it like this, just freehand. Okay, so this is my 79,400. There are two lines that meet at a right angle that would make up the legs of this right triangle. Because that's 45 and that's a right angle, this is obviously also 45. We're looking at an isosceles triangle here. So I don't even need to use sine and cosine to do this. I could just do Pythagorean theorem, right? And I could say a squared plus b squared equals 79,400 squared, and a and b are the exact same numbers, so it's more like 2a squared equals that. All right, so let me solve that for a second, and I will be right back. So what I got was 6.3 times 10 to the 6th, or 6,300,000, rounding it off a little bit there. When I squared 79,400, I divided it by 2, took the square root, and got 56,144 newtons. So that was the length of each side. Okay, if I found out the sides that would be necessary for this 79,400 right there. So let me drag this little arrow. Whoops, not that. Let me drag it. Oh, no, I don't want both. That's okay. Let me drag both. I got the 45 again. That's amazing. Let me drag it over and add it to my other triangle like this. And I didn't draw it perfectly, but it's kind of close. And I can see that the 79,400, the 56,144 is much farther over to the left than that blue 28,600 was to the right, if you can see that there. Okay, so the red is longer than the blue. So there's like this difference right here that I can get by subtracting the two numbers. All right, and that difference is going to be the horizontal part of my green triangle. And out of these two different arrows, the blue and the red, only the red goes upward. So the other leg right here, which is the other 56,144, hey, that must be the entire height of my green vector, my green arrow. So what I want to do now is make a green triangle, okay? So I'm going to make a green triangle, and so here is my green arrow, and I don't know how long it is. I do know something about the two sides of it. This side right here, that must be 56,144 newtons. It is one of the legs of my right triangle from the 79,400. And this little piece right here, this must be the difference between the 56,144 and the 28,600. Okay, if you subtract those two, that must be the length of that side. Once we have these two sides, we can then once again do Pythagorean theorem, okay? And when I've done Pythagorean theorem, I will find, hey, this is the net external force. And I'm running external kind of as a subscript to the F to say that this is not just any force, this is like my external forces of the wind and the waves buffeting our sailboat. So that is the number right there when you do Pythagorean theorem that you want to divide by the mass to find the acceleration that is the answer to our problem here, okay? So that problem had very little physics in it. What is the physics? The physics is F equals ma, this last step. Take that, divide it by the mass, you're done. The rest of it was a little bit of a geometry problem, okay? And we don't do that a whole lot in AP Physics, but it's good to have a basic command of sine, cosine, tangent, Pythagorean theorem, and just the ideas of triangles as we jump in, because we sure will be using that kind of geometry quite a bit throughout the year. So the answer for number 12, I guess specifically, is the resultant acceleration, and then the direction of it. It wants to know an angle. So you would have to specifically calculate either this angle or this angle in that triangle, right? And that would give us both the length of the arrow, and then the angle would give us the unique information about the vector. Its magnitude, that's the number, and its direction, okay? That's the angle. The next little one, number 14 here, I'm not going to go over to my notes page. This problem, you just want to use the very simple expression that the weight of something, that is the force of the Earth's gravity on it, is going to be equal to mass times its acceleration. And whenever we're doing the acceleration and we're talking about weight, that means that we're talking about the acceleration due to gravity. You may remember from freshman year, there's a special symbol we use for this, and it's a lowercase g. So A is usually what we use for acceleration, but when we discuss gravity's acceleration, and we're close to the surface of the Earth, and it's 9.8, then we have a special symbol that we use for that. Kind of like in math class, you use special symbols for things that are always the same number, like pi. You know, should know is 3.14. I don't know the rest of the numbers, but probably you memorized a few more. And so in the same way here, we use the G for a special number of 9.8. So I'm just going to take my given mass right here in this problem, multiply it by my 9.8, and I have the answer right away. When we take the same object and we go off to the moon, where we have 1/6 of the force of gravity, this is not very complicated. Divide it by 6, right, to get the weight of it on the moon. Now, number 15 asks you for the mass of it on the moon. You may remember that mass is a property that does not change as you move around the universe. And so the mass of it on the moon is the same as the mass on Earth. But gravity's effect on it is what we call the weight, and it's not the same. Okay, so 15, you would simply record 24 kilograms. 16 would record its weight, which would be 1/6 of that on the Earth. Okay, which we got from number 14. All right, I'm going to skip ahead here a little bit and let you work on some of the other problems. I think most of them are pretty straightforward. 22 and 23 are not. 22 and 23, I can tell you right now, you will be having a little assessment over the summer homework, during that first full week of school, likely, or the second full week of school. And when we're all ready for it, we'll take it. But these two questions, 22 and 23, will not be on it, not like this. This is, we'll set it up and look at how to solve it. But the algebra gets pretty annoying to solve this, unless you have a TI Inspire and you know how to use the solver in it, and you just crunch in the two equations and let it do all the work for you. But let's look at the situation right here, because this is a beautiful situation of something that is balanced. In physics, it is in what we call equilibrium. Equilibrium means that all the forces in a tug of war are perfectly balanced, and so it is not changing its motion. Okay, it is an equilibrium. And so it is being pulled down with a force of 9.8 newtons, and these two forces are pulling up and at angles. 5.5 pulls up left, 7.2 pulls up right, and I'm going to break these two forces, 5.5 and 7.2, I'm going to break them into triangles. So I'm going to have this 5.5 like this. I'm going to break it up into two little pieces. One piece going this way and one piece going that way. And then I'm going to take my 7.2, which I'm going to draw a longer arrow. That wasn't much longer. Let's make it a little longer. Okay, because 7.2 is more than 5.5, so we should have a longer arrow. And if I break that up, I get also two different legs of a right triangle there. Okay, now I'm really interested in these legs of a right triangle, and let me tell you why. If this is not going to move, this object in the middle, that means that the pull to the left of the 5.5 and the pull to the right of the 7.2 actually have to be the exact same amount of pull. Because if it was pulled more to the right or more to the left, it would move in the direction of the larger force. Also, the up and down pulls have to perfectly balance. So if I take how much is being pulled up by one and how much is being pulled up by the other rope supporting it, then these two upward pulls have to add together to equal our 9.8. Oops. Okay, so our 9.8 right here has to add up to equal these two upward pulls, because 9.8 is down, these two are up, it's not moving, it's in equilibrium, they balance. So this is going to be a math equation. It's going to be a math equation where I have a system of equations. That's two equations. One that tells me the two upward pulls have to equal 9.8, and the other one telling me that the left and the right have to equal each other. And so that is how we're going to approach the solution to this problem. Now, the reason I'm not going to solve it, I'll show you, is because, boy, it is a nuisance to kind of fill in all that information. Because your unknowns are going to be the angles in this situation for 22 and 23. So here we have alpha, let me double check, it is alpha, and the other one's alpha 2. Okay, so this is the adjacent side. So I'm going to say that this would be 5.5 newtons times cosine of alpha. If you're curious where I got that from, please note 5.5 newtons is the length of my hypotenuse in this case. These two are at right angles to each other. This is my adjacent side. So I can say cosine of my angle is equal to the adjacent side over the hypotenuse, which is 5.5 newtons. And if you multiply both sides of the equation by 5.5 newtons, it cancels out on the right. And on the left-hand side, I see 5.5 newtons times cosine of theta is the adjacent side. So I just put it in there, okay? By the same little process, you can do the opposite side over here and get 5.5 newtons times sine. And it's giving me a hard time right now. Times sine of my alpha, and that is the vertical side there. I'm going to go ahead and switch colors here for the, I think it's red actually, on the other page. Okay, so there's my 7.2. Okay, and this side right here is going to be 7.2 newtons times cosine of alpha 2. And this side here is 7.2 newtons times sine of alpha 2, where alpha 2 is the angle right here from the horizontal up to the rope that's going upward. So my two equations, let me write them down at equilibrium condition first, because what I've done so far is really just a whole bunch of math, not really physics at all yet. And so let me just say that the sum of the forces that are external in the problem, the ropes and gravity, they're going to have to equal 0. And I'm going to write this actually in two different equations. I'm going to break apart the x information. Okay, so rather than putting external there, I'm going to change that out, and I'm going to say, let me just look at the x forces. I'm going to say the x forces horizontally have to equal 0. And I'm also going to say over here, hey, all those forces in the y direction, they have to equal 0. And so when I look at the forces in the x direction, there are, once again, two of them. I have this one, and I have this one, right? Those are horizontal. So I'm going to put them here in my equation for the horizontal. I will say, let's do the green one first. We'll say 5.5 newtons times cosine of alpha. That is the force pulling to the left. Okay. From that, I'm going to subtract the force pulling to the right. And I'm going to get 7.2 newtons cosine alpha 2. And together, they're all going to equal 0. They're subtracted, by the way, because one pulls left, one pulls right, so they're kind of canceling each other out. All right. The next equation I want to put together is I want to put together the one for the vertical information. So for that, I have this side and this side. That we said those two numbers, 5.5 times sine of alpha, 7.2 sine of alpha 2, they have to add up to 9.8. That's gravity pulling down. All right, so I'm going to write that equation right there. And let's take the green element, the green component of that tension in that rope. I'm going to put a plus sign here. The reason I'm using plus is because they're both pulling upward this time. And then I'm going to put a minus sign, and I'm going to put in 9.8 because gravity is pulling down. Okay, so the upward forces get added together. The downward force gets subtracted because it's in opposite direction. And that is the equation. Now, this equation has two unknowns in it. Okay, so this equation has an unknown right here. That's one unknown, and it has another unknown right here. So I have two equations and two unknowns, and that we can substitute and solve this. What makes it difficult is when you try and solve for one of your unknowns in one of these equations, you're going to have an inverse sine or an inverse cosine of an enormous term. And then you got to drop it in the other equation. And if you do it all by hand, it's just a nuisance. If you have a TI Inspire and you plug in these things, you just say solve it, it'll do it for you, and you get two equations, two angles out beautifully. I'm not going to solve that right now because we've done the part of the problem that matters to me the most, which is the geometry of it. And we've also broken our forces into components. And I've said, hey, in equilibrium, they're all equal to 0. And so I set up my equations. The math work that is left is far too difficult for us to have done in class or to have put on an AP exam because you can't solve it without an awful lot of work or a really powerful calculator. All right. So that is the end of the second assignment. I'm going to go ahead and end the recording here. And I want to emphasize there's a lot of just crunching of problems here. And this is only a small portion of what we do in AP Physics. The purpose of the homework, again, is to bring to the front of your mind some basics of geometry and basics of problem solving. that we did do freshman year. And so these problems are more difficult than that, I understand. But I want to bring some of those basics back to mind again so that we are able to kind of start the year and refer to some of these things as we go along. And so if you struggle with this, that's because it's a little bit of a struggle. The third assignment is actually a little bit harder than this. Then the fourth and fifth get easier than the third, okay? So the summer homework is kind of like a little mountain, which gets harder and harder up to the third assignment, and then easier again on the fourth and fifth. And so we will consider all of those in the next couple of videos, but this is the end of the second one. So talk to you soon.